Hello everyone. I have an interesting integral here that with a trick it can be actually converted into an easy one. So we have negative 1 to the power of a times x um, and the integral of it times dx is of interest. So by the first inside, minus 1 to the power of ax seems to be alternative function that you cannot decide on the sign of it. So let's try to convert this one into a term that we can easily take the integral. So there is a beautiful formula in mathematics called Euler's formula. So Euler's formula is, so I'm just going to write it here. Euler's formula is basically e to the power of I theta. I is square root of negative 1 is always cosine of theta plus I sine of theta. So if we look at our integral, if we plug in pi into this formula, we'll have e to the power of I pi is equal to cosine of pi plus I sine of pi. From here, sine of pi is 0, 0 times I is 0, and cosine of pi is negative 1. So negative 1 is equal to e to the power of I theta. Let's go back and plug this into our integral. So we'll have integral of minus 1, which is e to the power of I pi, to the power of ax times dx from minus 1 to 1. We can multiply the exponents. We'll have minus 1 to 1 e to the power of I pi a x. So I put all the constant ones in the parentheses times x times dx, because the integral is basically based on the dx. So from here, this is a super easy integral then. Then the integral of exponential is always 1 over the coefficient of x, I pi a, and the exponential itself, I pi a x, from minus 1 to 1. Okay? So we need to just plug 1 and minus 1 into this into the outcome, which is 1 over I pi a is fixed e to the power of I pi a times 1, which is 1, minus e to the power of I pi a times negative 1. So I put a negative 1 behind everything. So this integral is solved, and this is the answer of it. But let's simplify this expression. So from the Euler's formula, if we if we multiply both sides by negative 1 and take the difference between them, you can find that this term can be expressed in terms of a sine or cosine function. Let's do that. So let's say that we have, from the Euler's formula, we have e to the power of I theta, which is cosine of theta, plus I sine of theta. And then we have e to the power of minus I sine of theta. It's going to be cosine of minus theta, but cosine of minus theta is cosine of theta, plus I sine of minus theta, which is going to be, which negative comes out of the sine. So it's going to be minus I sine of theta. Then let's multiply this by a negative 1 and and take the sum. So we'll have e to the power of I theta minus e to the power of minus I theta is equal to, cosines will cancel out, 2I sine of theta. And from here, we'll have that e to the power of I theta minus e to the power of minus I theta over 2I is equal to a sine of theta. Let's go back and see if we can rewrite the answer of the integral that we derived in terms of a sine function. So this will be equal to, if we multiply both numerator and the denominator of the of this fixed coefficient by 2, we'll have 2 pi a 2I over, and in the denominator we'll have e to the power of I pi a minus e to the power of minus I pi a. So this part, this term, is basically sine of pi a. So we can rewrite this term 2 pi a times sine of pi a. So basically sine of pi a over pi a is called sinc function. So sine of x over x is called sinc function. It has numerous applications in engineering and telecommunications. So as we predicted, the sign of the integral all depends on the value of a, and it's basically periodic. Thank you very much for watching.